Uh, Good morning to all. This is Anvesh from AAA branch. Uh, today, my- uh, Today my topic is about energy minimization and Kirchhoff law in negative capacitance, ferroelectricity, capacitors, and MOSFETs. Coming to the introduction, the energy efficiency is a big challenge in modern integrated circuits, and new switches with a sub-threshold swing below 60 megavolts decades are necessary to reduce. Thoroughly investigated recently years, with promising experimental results being reported and with a large technological potential due to the fact that HFO2 exhibits robust ferroelectricity. The working principle of NCFETS is using the negative capacitance of a ferroelectrical insulators to convert a change of delta Vg. Uh, this paper reversed the physics between such capacitor networks and two different or equal fundamental perspectives such as the Gibbs energy minimization of overall system and the Kirchhoff law used to connect the individual capacitors. Now coming to theoretical conditions. Yes, now coming to theoretical conditions, T. Rollo and D. Ensign are with the Departamento Politician D. D. University of Udine, Italy. Sorry for the disturbance. Is a where if you see the equation here, TFEP naught delta P by delta T plus dou U by dou P into GFE equal to 0. So where P is a polarization charge and dou is a resistivity describing the dissipation associated to the ferroelectrical domain. Switching the GFE is a Gibbs free energy. The total charge Q at the ferroelectrical interference is Q equal to P plus E naught EFE. And if you see the equations of these are very tough. For the process of implances, no change is either temperature or strain conditions. The variation of Gibbs free energy due to the application of external stimuli may be written as like this. So, where alpha and beta or gamma are the parameters of electrical materials, and VFEQ is the energy variation in the voltage source. So, next, may be interpreted as a static voltage charge V of Q characteristics of ferroelectricity capacitors. So this is the equation of this given below. So this is the diagram of this given topic. So if you see the figure 1 sketches of a series of FEC and possible non-linear NFC connected to a voltage supply, though through an electronic switch, same as B. So where C is a capacitance per unit area for such a linear capacitor, the Gibbs free energy is given by this formula. And by setting, we now come to the main point of the paper and consider the series of ferroelectric FEC and non-ferroelectric capacitors NFEC isolated in a figure 1. When conceived two different approaches to calculate the steady state charge Q and the potential VC at the internal load. So this is the equation VFEQ plus VFE is not equal to VT. So we have so many equations in this. And now coming to numerical results, we verified the main conclusion of the previous section by using numerical simulations for the NCFET sketches. In figure 1, all simulations were carried out for a ferroelectrical HFO2 layer with TFE equal to 20 nanometers, and with a steep retrograde channel doping profile to improve the capacitance matching conditions. It should be noticed, however, that is an NCFET, the capacitance matching is influenced by a number of capacitance other than the intrinsic semiconductor's capacitance, such as the source drain parasitic's capacitance and the parasitic's backend capacitance. While these capacitive terms are very important for the device design, they do not influence the main conclusions of this paper, cornering the equivalence between energy minimization and Kirchhoff law. The parameters of LKE for the ferroelectric HFO2 are alpha equal to minus 3.9 E 8 ME by F, and then beta equal to 1.0 E 10 meter per 5 F F dash C square, and gamma equal to minus negative 2.65 electrovolts 10 to the power of 9, and they have been extracted from a best fit for the experimental V versus EFE curves reported in such as parameter representative of PEFE characteristics is corresponding to the periodic regime that establishes after the expiration of a possible wake-up phase of ferroelectrical materials. In the NCFET of the NFEC is given by the semiconductors with 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 being respectively the potential and the charge of NFEC. We model the system by solving 1D Schrodinger equation in the semiconductor with a parabolic effective mass Hamiltonian. So these are the graph of velocity v and q charge. So these are the variations of graphs that this experiment has. So this is the information that we provided, that they provided in this below paragraph. And the main meant and the material parameter of a silicon interface and the material parameter of a silicon interface, the electron wave functions, and then used to determine the equilibrium electron density, and the 1D Schrodinger and Poisson equation are solved self consistently. The FEC is described with a steady state LKE equation 4 and linked to the underlying semiconductor through the conductivity of the electric displacement, where Z is the electrostatic potential and Z is a vertical direction. If you see in the figure C, yes, it's worth nothing that such methodology methodology is conceptually equivalent to the first approach described in section 2, namely to the minimization of the Gibbs free energy of the ferroelectric alone, followed by the Kirchhoff law. And thanks to negative VFE across the ferroelectric, in order to verify whether or not the Q values in the figure 2 correspond for any give Vg to a minimum of the Gibbs free energy of the overall system, we employed equation 9 to calculate the energy. So this is the equation that we get by the conclusion, and then analyze the total Gibbs energy and illustrates as well as UFEQ and USC versus Q for VG and VG2 equal to 0.35 closely. So where it can be seen the charge values, the minimizes GD for VG1 and VG2 coincide exactly with the corresponding values in figure 2, and also shows the while CSC is quite constant and USC is approximately parabolic in a Q range between 0.5 to about 2 mu coulombs per centimeter square. For large Q values, the honest of the inversion is clearly observed in the CSC behavior, and consequently USC deviates remarkably from a parabola and actually approaches a linear behavior. The CSC changes the changes by almost by a factor of 2. For example, when Vg increases from Vg1 equal to 0.15 volts to Vg2 equal to 0.35 volts, hence it shows the equivalence between the two methodologic methodod, met- methodologics to describe the FEC and NFEC series connections holds in the bias range where CSC is significantly non-constant. The that is for a significantly non-linear capacitor. The results have been verified in very main different conditions including different TFE and doping profiles, the bulk NCFET of figure, and also for NCFET in the silicon on insulators films, and thus consisting of three capacitors in the series. So now the conclusion. This paper has demonstrated that within the validity limits of our analysis, the description of FEC and NFEC series based on the minimization of Gibbs free energy of ferroelectric alone, followed by the Kirchhoff law, is equivalent to the minimization of Gibbs free energy of the entire system. Our analysis, however, has introduced a few simplifying assumptions. We assumed a uniform polarization and used a one dimensional LKE which neglects surface effects and multi domain effects that have been shown to the important. For example, in comparison to experiments of ferroelectrical capacitor switching, further works is necessary to investigate of the topic of paper under more generally conditions. However, we believe that our conclusion holds for those numerous papers in the literature that approach NCT simulation using approximately similar to the ones employed in this work. So, uh, the the acknowledgement is the authors would like to thank Professor Sumant Datta for fruitful and simulating discussions, and you can be for more information you can be use this reference books that over here, the 22 books. So this is my topic about energy minimization, Kirchhoff law in negative capacitance, ferroelectrical capacitors, and MOSFET. Yes. Mainly, these diagrams are important for this experiment. If you see the diagram A, we connect a switch and FE and FC. So these are very important. So this is the topic I have explained. So I hope all of you have understood my topic. So thank you.